The nuclear reactor is the most powerful and heavily contained machine on Earth. It captures the fierce energy of the atom to power civilization. This process is a masterpiece of containment. The goal: control the fierce chain reaction and safely transfer the resulting heat for electricity. Our deep dive begins at the fuel uranium, precisely packaged into small pellets and sealed within metal tubes called fuel rods. The energy release mechanism is nuclear fission. A neutron strikes a uranium nucleus, causing it to violently split. This fission releases intense thermal heat and critically more secondary neutrons. This is the moment the chain reaction begins. If left unchecked, the reaction would run away instantly. The power must be regulated by control rods, the safety brake of the reactor. Control rods absorb the excess neutrons. Lowering them slows the fission rate. Raising them increases power. They are the constant fission counterbalance. The moderator, often pure water, must slow down the fast neutrons released by fission, allowing them to be captured by the fuel. The immense heat produced by fission must be removed and converted. This is the role of the primary coolant system. The pressurized coolant prevents boiling, allowing it to reach superheated temperatures without changing phase, critical for high-efficiency heat removal. The heated primary coolant is pumped through the steam generator, transferring its heat to a separate, isolated secondary water loop. This heat instantly flashes the secondary water into high-pressure steam, clean and completely non-radioactive, the final power carrier. The high-pressure steam drives the steam turbine, a massive mechanical machine that converts thermal energy into electrical rotation. The turbine's rotation is coupled directly to the generator, which converts mechanical energy into electricity at grid frequency. After exiting the turbine, the steam enters the condenser, where it is cooled and returned to the steam generator as pure water, completing the thermal cycle. The cooling towers manage the waste heat, releasing clean water vapor. The safety of the core process relies on continuous heat rejection. The ultimate safety check is the emergency shutdown. Scram. This mechanism is activated by any severe sensor deviation, prioritizing core protection. At the signal, the magnetic clutches holding the control rods are instantly released. Gravity slams the rods into the core to stop the fission. This action stops fission, but a major threat remains: decay heat, residual heat, still being released from fission products. Heat removal must continue. The emergency core cooling system, ECCS, activates. High-pressure pumps inject massive amounts of cold water to combat this decay heat. The ECCS ensures that even after Scram, the core will never be uncovered, safeguarding the fuel from meltdown, the critical safety failure. The Containment Dome is the final, massive safety layer. It is a sealed fortress designed to contain all radiation and pressure. The operation of a nuclear plant is a daily miracle of control and safety, managing the fiercest power of the atom with human ingenuity. If this deep dive into nuclear engineering and complex safety systems intrigued you, please take a moment to hit the like button.